Hi, I'm Ala, and in this presentation, I'm going to talk about limitations of noisy quantum circuits and the space overhead necessary for fault-tolerant quantum computation. This is based on a joint work with Omar Fawzi and Alexander Müller-Hermes. As you know, quantum resources have been proven to provide a considerable advantage in certain computational tasks. But quantum systems are extremely fragile, and quantum computation is inherently noisy. And that's why when the first quantum algorithms were discovered in the 90s, people were very excited, but at the same time, mostly skeptical about whether we can ever actually implement these algorithms. And at the time, quantum error correction seemed to be simply impossible because the ideas from classical error correction did not seem to be useful to protect quantum information. And this was until Shor and Steen introduced the first quantum error correcting codes in the mid-90s. And this was the beginning of the theory of quantum error correction and fault tolerance as we know today. Perhaps one of the most influential results in the theory of quantum computation is the fault-tolerant threshold theorem, which states that you can do arbitrarily long quantum computations on a noisy quantum computer as long as the noise level in your quantum computer is below a constant level, which is known as the threshold value. Of course, I haven't defined what I mean by the noise level or how we model noise on a quantum computer. And in fact, the threshold value actually depends on the details of the model we consider, both the noise model and the circuit model. But this is great, and what is even more remarkable is that we can achieve fault tolerance at a very reasonable cost. So there exists a fault tolerance scheme which maps any circuit of width n and depth t to a fault tolerant implementation circuit of width n prime and depth t prime, such that the overhead is only polylogarithmic in n and t. And we define the space overhead as the ratio n prime over n, and the time overhead is defined as t prime over t. Okay, so this is very nice. The overhead seems very reasonable, but then why is it that we haven't been able to perform more interesting quantum computations yet? Well, one of the problems is that the overhead of the known schemes is still too much for today's technology, and our implementations are still too noisy. So, broadly speaking, the results on fault tolerance are in two main directions. The first class of results are achievability results, which aim at introducing more efficient fault tolerance schemes with lower overhead and a higher tolerance to noise. There are a lot of results in this direction, and I have listed a tiny number of them here. In particular, more recently, Gottesman showed that assuming good quantum error correcting codes satisfying certain properties exist, then the space overhead can be asymptotically brought down to a constant. And later on, Fawzi et al. Proved that quantum expander codes actually satisfy these desired properties and actually showed that constant space overhead is indeed achievable. However, in contrast to the threshold theorem, which applies to arbitrarily long circuits, this scheme achieving constant overhead only works for circuits which have depth at most polynomial in the width. And so this motivates the following question. Given a noise model, how does the necessary overhead grow as a function of the circuit size? So the second class of results on quantum fault tolerance are concerned with questions of this type. So these are impossibility results, which study limitations of noisy quantum computation and fault tolerance. And here, our understanding is very limited. And this is partly because it's not really easy to define what a fault tolerance scheme is. And so in this work, we studied the question I mentioned earlier, And in doing so, we try to address some of the limitations of the earlier results, which I'll discuss in detail in the next slide. Okay, so I've been talking about noisy quantum circuits. So let me define what our model is. So in our model, a quantum circuit is simply an ordered sequence of quantum channels or completely positive and trace preserving linear maps acting on a potentially non-trivial input system. We use the term time to refer to the vertical paths between layers of computation as shown in this figure. The number of qubits may vary in different time steps. So in each time step, fresh ancilla qubits may be added, qubits may be measured, and the measurement outcomes may be processed, and the next operations may depend on this information. And for reasons which become clear in the next slide, we distinguish between classical and quantum subsystems. So in this figure, we denote the classical subsystems by double lines. So for the noise model, we consider IID noise, where in every time step, every qubit is subject to some noise channel N. And an important feature of our result compared to the previous results on limitations of noisy quantum circuits is that we allow classical computation to be noiseless. And this is important because today we can do classical computation with practically perfect accuracy. And in fact, in our model, classical computation is free and noiseless. So we use the notation IID sub n of C to denote the quantum channel corresponding to the noisy implementation of a circuit C in the IID noise model, where the noise is modeled by this qubit channel N. So we are ready to state our main result. A unitary quantum channel is a channel that conjugates its inputs by a unitary operator. So a unitary channel is not an interesting noise channel, especially in our circuit model, because we can perfectly cancel the noise by basically applying the inverse unitary operator. So our main result is the following. So let n be a non-unitary qubit channel. Then for any fault-tolerant scheme against the IID n noise model, the number of physical qubits, or n prime, is at least the maximum of the following two bounds. The first bound is alpha n times log t, where alpha n is just some constant only depending on the channel n. And the second lower bound is the inverse of the quantum capacity of n times of the channel n times n. So the quantum capacity is basically the maximum rate at which quantum information can be transmitted using this noise channel n. So in fact, if n has zero quantum capacity, or the space overhead is less than the inverse of the quantum capacity of n, then you cannot achieve fault tolerance even for a single time step. And as we'll see, this is a direct consequence of our model of fault tolerance, which I will define in the next slide. So for the rest of this talk, I'm just going to focus on the first bound, alpha n times log t. Okay, now in order to prove a statement about fault-tolerant schemes, one first needs to define what a fault-tolerant scheme is. And as I said earlier, it's really difficult to provide a definition which captures all the different aspects of fault tolerance. Here, we consider a very natural model of fault tolerance with minimal assumptions that, as far as we know, are satisfied by most, if not all, the known schemes. According to our model, a fault tolerance scheme is only required to be capable of implementing any arbitrary circuit on encoded data in some code space that is associated with the fault-tolerant scheme. More precisely, a fault-tolerant scheme is a family of circuit encodings indexed by L associated with a family of quantum error correcting codes with encoding and decoding maps E and D, again indexed by L, such that the following condition is satisfied. Given any input circuit C and any accuracy parameter epsilon, a fault-tolerant scheme should output an encoding of C from the family for sufficiently large L such that the encoded circuit is fault-tolerant in the following sense. So if we consider the quantum channel corresponding to first applying the encoder and then the noisy implementation of the encoded circuit, and then followed by the decoder, the overall quantum channel is epsilon close to the quantum channel corresponding to the original circuit C. So here we take the induced trace distance as our distance measure. Note that the encoder and decoder are assumed to be ideal in our model. To understand the definition better, you can think of fault-tolerant schemes based on concatenation. And in this case, the index L corresponds to the level of concatenation. So in order to prove our main result, we prove the following lemma, which is our main technical contribution. So we fix the qubit noise channel N, and we consider a quantum circuit of depth T and width N such that the registers in each time step are partitioned into A and B subsystems, and the circuit is only allowed to act locally on A and B subsystems. And it is only allowed to communicate classically between the A and B parts. So for any such quantum circuit, we show that the amount of entanglement between the A and B parts is decreased by a factor of 1 minus p to the n, where p is a constant only depending on the channel n. Here we let rho I denote the state of the circuit after I time steps, and as our measure of entanglement, we use chi-sap, which is defined for state rho AB as the minimum chi-squared divergence from the set of several states with respect to the partition AB, and the chi2 divergence between two density operators rho and sigma is defined by this equation. So here's our lemma. From the lemma, we can prove the following corollary. What does this corollary say? It says that for any non-unital qubit channel n, there exists a constant p depending only on the channel n, so the same constant as in the lemma, such that any circuit of depth t and width n with t at least 1 over p to the 2n is not capable of preserving even a single qubit. This is true even if the qubit is encoded perfectly in some quantum error correcting code and we have an ideal decoder. And so our main theorem follows from this corollary with alpha n equal to 1 over 2 log 1 over p. So I'm going to at least give you an idea of how we prove the lemma I mentioned in the previous slide. But before that, let me discuss some of the earlier results on noisy quantum computation that are relevant to our work. So Benor et al. Studied noisy quantum computation with no supply of fresh ancilla qubits. Similar to us, they consider the IID noise model with different qubit noise channels n. In the case of depolarizing noise, they show a logarithmic bound on the maximal length of computation. Their proof is based on an entropy production argument, and So in our model, we allow fresh ancilla qubits to be introduced during the computation, and we also allow intermediate measurements. And this allows us to remove the entropy produced by the noise in each time step. And as a result, arguments of this type are no longer applicable in our model. And then for dephasing noise, they prove a polynomial lower bound and upper bound on the maximal computation time. Their argument for this case has a similar favor to our proof, but it's in a more restricted circuit model with no fresh ancillas available. And finally, for amplitude damping noise, they show how to do quantum computation for an exponential time. And they actually conjecture that an exponential upper bound should also hold, and they pose it as an open question. Here in this work, we prove an exponential upper bound even when fresh ancilla qubits are available. So our upper bound is exponential in n plus m, where m is the maximum number of ancillas that are used in different time steps. Another relevant result is a work by Roginski, who studies the same problem in a different model. In his noise model, he assumes that a fixed, strictly contracted noise channel acts collectively on all the qubits in the quantum circuit after each computational step. So a quantum channel is said to be strictly contractive if the channel strictly decreases the distance between any two input states. So he showed that for any circuit involving only unitary gates, the distance between any two input states decays by a constant factor in each time step. Our work can be viewed as an extension of this result. In particular, we show how to apply a similar reasoning when the noise is given by tensor powers of arbitrary non-unitary qubit channels. And we also take into account free and noiseless classical computation. Then we have a sequence of results on noisy quantum computation that are maybe not directly relevant to our work. These results prove statements of the following form. If the noise level in a quantum circuit is higher than a constant level, then the circuit is useless after a bounded number of time steps. Now, if you recall the statement of the threshold theorem, it said that you can do arbitrarily long quantum computations if the noise level is below the threshold. So these results apply only to noise levels above the threshold value. In fact, they prove upper bounds on the threshold value. Whereas in our case, we do not put any restriction on the power of noise. And this is exactly the reason why we can translate our results to a statement about the overhead of photon schemes. Another point is that in these works, there is no distinction between classical and quantum subsystems. And classical systems are also subject to the same noise. These results also consider different measures of uselessness. For example, Razborov shows that under strong depolarizing noise, after a logarithmic number of time steps, the output of any circuit will be basically independent of the input. Kempe et al. Also prove a similar statement, although in a slightly different model. However, if we allow noiseless classical computation, then these statements no longer hold, even for arbitrarily long circuits. For example, you can consider a circuit where a subset of qubits are measured in the first time step, and they're kept noise-free and output at the end of the circuit. Then the output is no longer independent of the input. And finally, these results are mostly focused on depolarizing noise, with the exception of the work by Vermani et al. And it's not really clear how the techniques can be extended to other noise models. Finally, let me point out that our result also implies an upper bound on the threshold value for ID noise modeled by different qubit channels. For example, in the case of P depolarizing noise, which with probability P maps the state to the maximally mixed state, and with probability 1 minus P keeps the state intact. It's known that the quantum capacity is 0 for P strictly greater than 1/3. Therefore, in our model, fault-tolerance is not achievable for a single time step, which implies an upper bound of 1/3 on the threshold value. This bound is actually stronger than the previous bounds given these earlier works, except maybe a bound by Kempa et al., which is under specific assumptions. But I should say that these results are not really comparable because the models are different. So as I promised earlier, I'm going to very briefly explain the outline of the argument we used to prove our result. So let's recap the setup. We have a quantum circuit in which registers in each time step are partitioned into A and B subsystems. The circuit only acts locally on A and B, and it communicates classically between the two parts. And our goal is to show that the entanglement between the two parts of the circuit decreases by a constant, by a factor of 1 minus p to the n in each time step, where p is a constant only depending on the channel n. So we use two different arguments for the case when n is unital and when n is non-unital. So a quantum channel is unital if it maps identity to itself. We show that any non-unitary unital qubit channel is slightly entanglement breaking in the sense that it can be written as a convex combination of a unitary channel and an entanglement breaking channel. So a quantum channel is called entanglement breaking if it's when it's tensored with identity, always maps to separable quantum states. So given this lemma, it's easy to see how the proof goes. So in each time step, with some probability p to the n, the entanglement between the two parts of the circuit is completely destroyed. And we can show that the entanglement is reduced by a factor of at least 1 minus p to the n. In order to show this key lemma, we use the block sphere representation of qubit states. So the Pauli operators form a basis for the set of 2 by 2 Hermitian operators with respect to the Hilbert-Schmidt inner product. And any single qubit state rho written in this basis is represented by a vector r in R3, which is called the block vector corresponding to the state rho. Now, in this representation, the action of any qubit channel up to unitary rotations corresponds to first rescaling R according to some vector lambda in R3, and then shifting it by another vector T in R3. It's easy to check that such a linear map is trace preserving, but for it to be completely positive, T and lambda need to satisfy some constraints. And it turns out that for unital qubit channels, we have necessary and sufficient conditions for this. So in this representation, a linear map N is unital if and only if T is equal to 0. And theorem 1 here by Ruska et al. States that up to unitary rotations, the set of unital qubit channels can be described by a tetrahedron in R3 with corners that are given by these 4 points. And these points actually correspond to conjugation by Pauli operators. And the final ingredient we need is another theorem by Ruskay, which states that unital qubit channel is entanglement breaking if lambda in this representation belongs to the convex hull of these 6 points. And these are exactly the midpoints of the corners of the tetrahedron in theorem 1. So this convex hull is an octahedron which is inscribed inside the tetrahedron. Now, using this geometric picture, it's easy to see that any unital channel can be written, unital qubit channel can be written in the form of the lemma, and the constant p is easily computable using a simple linear program. Next, we consider non-unital noise. Um, we first need the following definition. The trace norm contraction coefficient of a quantum channel n is defined as the supremum over pairs of density operators rho and sigma of the ratio given by the trace distance between n of rho and n of sigma divided by the trace distance between rho and sigma. So a quantum channel n decreases the distance between any two input states by at least eta trace of n. And as I mentioned earlier, a quantum channel n is called strictly contractive if eta trace of n is strictly less than 1. So you can show that non-unital qubit channels are examples of strictly contractive quantum channels. And this can be seen, for example, using the representation in the previous slide. Now, the idea in this case is to use this fact to show that the noise in the circuit decreases the distance from the set of separable states in each time step. But we need this contractivity property for tensor powers of the noise channel. Unfortunately, in general, if a quantum channel is strictly contractive, its tensor powers are not necessarily strictly contractive. For qubit channels, however, this is not the case. In fact, we show that for any non-unital qubit channel n, there exists a constant p depending on n, such that the trace norm contraction coefficient of n tensor n is at most 1 minus p to the n. I believe that the fact that tensor powers of strictly contractive qubit channels are strictly contractive was actually known before, but our contribution is that this quantitative statement about how the contraction coefficient behaves under tensor powers. To show this, we prove a general upper bound on the trace norm contraction coefficient in the d-dimensional case. The bound is in terms of the minimum eigenvalue of the Choi operator corresponding to the composition of the channel with its adjoint, defined here. If you're not familiar with this, just think of it as a PSD operator defined by the channel. So what is nice about this bound is that it behaves nicely under tensor powers of channels. So this operator for n tensor n is equal to the operator corresponding to n tensor n times. So the eigenvalues also behave as we want under tensorization. And we can also show that for non-unital qubit channels, this operator is full rank. So the minimum eigenvalue is strictly positive. Okay, so this would have been sufficient to prove what we want if the noise were acting only on all the subsystems. But in our model, the classical subsystems are noise-free. Intuitively, this shouldn't change anything because these are classical systems, and indeed, we have the same behavior, but for technical reasons, we need to use the chi-square divergence as our distance measure instead of the trace distance in order to deal with these noise-free classical systems. We also use this property that chi-squared contraction coefficient is bounded above by the trace norm contraction coefficient, where the contraction coefficient in this case is defined as before, with trace distance replaced by chi-squared divergence. So to summarize, in this work we studied noisy quantum circuits, and we proved a lower bound on the space overhead of fault-tolerant schemes. And we tried to address some of the limitations of the previous results. We consider a model with minimal assumptions. We allow classical computation to be free and noiseless. And so as a result, our results apply to adaptive protocols composed of a hybrid of classical and quantum computation. And our results also apply to the low noise regime, as well as the noise levels beyond the threshold value. And along the way, we also proved an exponential bound on the maximal length of computation against amplitude damping noise, which was posed as an open question earlier by Benor et al. So let me also mention a few open questions. So we have two bounds in terms of the circuit depth and width. Ideally, we would want a single bound which captures the dependence on both. Another direction is investigating the effect of adding geometric locality restrictions in the circuit model. So in our model, we allow arbitrary gates that act potentially on all the registers. However, in real-world implementations, we are always restricted in the number of qubits that we can interact simultaneously, and we can only act locally on qubits. The question is, with this additional restriction, can we show stronger lower bounds on the necessary overhead? And finally, we can consider a qubit case and noise channels in higher dimensions. So our techniques give us similar bounds for a subset of noise channels in a given dimension, but they're not applicable to all quantum channels. And with this, I'd like to conclude my presentation. Thanks for your attention.